Nucleophilic substitution is breaking sigma bonds and making sigma bonds. So keep it simple, right? So there are two types. I'll be talking about one first. So let's see. So if you have an organic molecule with sigma bonds, and we're going to focus on SN1 reactions, that is nucleophilic substitution 1. 1 means actually uni. So let's call it unimolecular substitution reactions or unimolecular nucleophilic substitution reactions, right? SN1. So this is the way we want to look at it in a concise manner. So we take a carbon compound and it has sp3 carbons, and iodine is considered as a leaving group, and sp3 has 4 different bonds, and there's hydrogen, there is an R group, some sort of CH3 C2H5 group, right? And that's, sometimes I call it substrate, sometimes you call the electrophile, right? And now, so let's see what we can react this with, right? And so I put R1 and R2 just to see it's different, right? So it might be a methyl group and an ethyl group. So when the reactions takes place, this is what happens. So let's say we use HOH, which is water. So the water is considered as a weak nucleophile. Why? Water has lone pairs to give away to make a bond, but it doesn't have charges. Now, if you look at the iodine is delta minus and carbon is delta plus. Carbon is the electrophile. So therefore, iodine steals the electrons and walk away, we call the leaving group. So it is happier when it gone away and as I minus. That is why Lg, the leaving group, right? So what's the product looks like? So we will not be getting a complete product. What we will get is this one, right? Let's see. So now, because we broke the top bond, sigma bond, and it ended up with the empty p orbital. That's why the p orbital with the plus sign. So there is no electrons in it. So we call it empty p orbital. Okay. Now, so another thing, if you can remember, this empty p orbital sitting this molecular species is an ion. It's called the carbocation, right? Carbocation. And the carbocation is in sp2, which is trigonal planar. So the shape is actually important in this case, because trigonal planar means it's flat, and you can actually have 2 different types of reactions. So the trigonal planar is flat, just like your phone. It has a top side and it has a bottom side, right? So let's see why it is important, right? As we go, so let's take a reaction. So now there's another thing happening. I said the weak nucleophile, it wasn't reacting at first. Now you have a reactive carbocation, empty p orbital asking for electrons. So these electrons can come from top, and it'll give you a different products in purple color I'm putting, or it can also attack, the weak nucleophile can attack to the carbocation from the bottom. So that would be a different product. So there's 2 kinds of products we can expect. One is came from because of the top attack, the other one because of the bottom attack in pink, right? So okay, so let's see what they are. So you just copy the blue area, which is sp2 carbocation, first copy, and then stick the water on the bottom and on the top as we expected. Now there's a little part I just neglected. In the water HOH, there is a hydrogen extra. I just neglected that one. Okay, so in the SN1 reactions, it's not a big issue about the proton exchange. So this is the important thing. So you draw the normal sp2 trigonal planar species and then stick the OH or the nucleophile from the top or from the bottom. So you're going to get two products, right? Now we can, once we complete this one, let's finish this. And what has happened actually, they looks like both the top product and the bottom product looks like object and then mirror image, right? It's an object and mirror image. So this is a pair of enantiomers. When you do pair of enantiomers in 1:1 scale, or we can say 50% each, and that would give you a racemic mixture. Or simply remember, 1:1 of the pair of enantiomers will make a racemic mixture. Now if you need a little bit more, this is optically not active because it cancels the top product with the bottom product. This is an important thing when we're talking about. All right, so now let's look at a little bit more about the shape, the graph of the potential energy graph. So I just draw kind of like an elephant, if you can see that way, right? See, the elephant has so the tail side is the product, and the trunk front side is the reactants, and then little valley on the top, in the middle actually, it is the carbocation intermediate. Why the intermediate is in a valley? Just think carbocation actually exists. Now the other thing is activation energy for the first reaction is pretty high, and because it's a big mountain to climb, it's a rate determining step, so it's a slow step. Now after the carbocation, that's a fast step, right? Okay, so we can say the first step of this series of reactions, rate determining step, is slow. After the carbocation is formed, the next is fast reaction. So that's why it's a little hump for the fast reaction, big hump for the slow reaction. So the two steps, right? Now, so we can also mention about the rate of the reaction. So now, if I opt in the RDS is the rate determining step, only thing you have there is the electrophile, sometimes we call the substrate. So therefore, the rate is equal to K, the rate constant, to the electrophile only, because if you remember, it's a unimolecular. It's only one thing is important for the rate determining step. And we said nucleophile is weak, so it's not really doing much there. So uni means one. Just remember, 1 and then 2, right? So therefore 1 unimolecular gives you 1, right? And therefore it's 2 steps. Uni means 1, it gives you 2 steps. Think like that. Okay, so that's it.